The next topic is introduction to simple stress and axial stress. Okay, let's begin. Once again, let's have an intro. So, recall, analysis of rigid bodies is concerned with the external and internal reactions of a body, right? In mechanics of materials, we analyzed internal forces, which are forces that act on cross sections that are internal to the body itself. Now, within that, we have your strength of materials. So, strength of materials is a branch of mechanics that deals with the internal effects of external forces on bodies, where internal forces are the forces acting at any section of a body necessary to balance the external forces to maintain equilibrium. In your statics of rigid bodies, we only discussed the external effect of forces. Now we're going to discuss the internal effects of forces. In short, we're talking about deformation. Okay? Now, the kind of deformation or effect that we're concerned with is stress. Okay? Specifically, simple stresses for now. So generally, stress is the force per unit area on a body that tends to cause it to change shape. General equation is sigma equals F over A, force per area. F is applied force. Okay? A is cross-sectional area over which the force acts. So take note of those definitions. Now, the common units that we'll use are Newton per millimeter squared or just MPa. Okay? Most of our answers will be in MPa, okay? So make sure to familiarize yourselves with the conversions. Now, within stress, we have two general types, one of which is simple stress. Simple stress is also known as direct stress. Now, under direct or simple stress, we have two types. First is the normal or axial stress. Next is the shear stress. Let's start with normal. Normal or axial stress is the stress acting in a direction perpendicular to the area. Now, within that, we have two more kinds. First kind of stress, it's the stress that is the result of actually loaded forces pointing towards the center of an object. The other one is caused when actually loaded forces are pulling away from the object's center and perpendicular to the object's surface. Now, based on the definition, what is the first one referring to? What do we call this first kind of stress? Correct, it's compression stress. Correct, Julia and Viren, or V. Santa Maria and Gonzalez. You're correct, it is compression. Now, what about the second one? What is that? Correct, it's tension. Correct, Vincent, Ursha, and Sierra. Gutierrez. Gutierrez. Sierra. And then Vincent. Tension. Just like our forces, okay? Towards your object, compression, away from your object, tension. So same thing applies to stresses. And then shear stress is just caused when the forces applied to an object are parallel to the object's cross-section. So basically, the main difference between normal and shear, normal is perpendicular to the area in question, shear is parallel to the area in question. Now let's talk about your normal stress. So when we have a compressed or compression stress, okay, what happens there is your material is compressed, meaning your volume is reduced, right? While for tension, since your material is being elongated, there's an increase in volume. So that is a deformation made for normal stresses. Compaction and elongation or expansion. Now, some examples for each type of stress are as follows. First, we have your cable cranes. They carry tensile loads in the wires. Okay. So therefore, these wires experience tensile stress or tension stress. Next, we have log columns carrying compressive loads. So generally, columns are great for resisting compression, but they act very poorly when resisting tension. Okay. And then next, we have rivets in your bridges or truss, which carry shear loads, because for these rivets, the forces are along the members, right? So this way, you can imagine that these forces are parallel to the cross-section of your rivets. That's why it carries shear loads, hence experiencing shear stress. I've mentioned earlier that wood columns or even just concrete columns are poor in tension. That's why we have reinforced concrete column. So reinforced concrete column looks like this. Okay, just a concrete pillar reinforced with steel or other materials that are great for tension. So the concrete portion of this is used to resist compression loads, while the steel bars are used to resist tensile loads. Okay, so we take into account several types of stresses when building or when constructing certain structures. Next, we have the second type of stress, which is indirect stress. Recall previously we had direct or simple, now we have indirect. So types of that are bending and torsional stress. Bending stress are seen in longitudinally loaded objects, so your frames. Next, torsional stress, it's shear stress produced in a shaft due to the twisting. So for now, we're focusing on direct stresses or simple stresses. Later on in the course, Module 2 and 3, we'll talk about these indirect stresses, okay? So this is an illustration or summary of what we've talked about. So if you have an axial load or axial force, it creates axial stress. It can either be tensile stress or compressive stress, and it looks like this. So you have force away from your body. So this produces tensile stress. And this is your cross-sectional area. Your force is perpendicular to it. Next, you have your shear force, creates transverse shear stress. Once again, we have this cross-sectional area. We have our forces parallel to it. Next, we have our bending moment, creates bending stress. So bending moment, same as moment. If your moment is like this, okay, it's gonna cause stress with your member. This is usually a beam. For this type of scenario, your beam will experience tension stress at the top, and then it will experience compression stress at the bottom. And then lastly, torsion creates torsional stress. So let's say you have a cylinder here, take an element inside being twisted this way. If you take the cross-sectional area of that, the stress diagram will look like this. So stress denoted by tau for torsional stress is greatest at the surface. As you can see by the diagram, then it turns to 0 here at the center of your cylinder. And those are the general stresses from your loads. Okay. So next we'll focus on your normal or axial stress. So axial stress is stress developed when the force acts normal at the center of gravity of a sectional area. You'll see that the equation is sigma equals P over A. It's almost the same as your stress equation, sigma equals F over A. That's because all of our succeeding equations will come from that general equation, sigma equals F over A. The difference here is F is not just any kind of force. For axial stress, F is a specific force P, where P is applied normal force. So it's the force that is perpendicular to your area. And then A, cross-sectional area over which the force acts. Okay? So sigma equals F over A general. Sigma equals P over A. P is your normal force. That's now for axial stress. Now let's talk more about that. Now what if I have an inclined plane? How do I get the stress of that? So these are our equations for a stress on inclined plane. So to derive that, let's do the following. Okay. Actual stress. Okay. So let's say we have this object, right? We have an applied force here. Okay, it's your F. Now, the stress that we're concerned with is on this inclined surface. Okay, let's call that A. And then we're given also an angle. So we're given this angle from the cross-sectional area to be theta. So let's call this your A. So capital A, cross-sectional area. Small a, the slanted area. Okay? So let's solve first for normal stress. To get normal stress, let's try to draw it. So I'm going to extend that line of action. It's going to hit here. Okay? Then let's get the components of your force. This is your F. Components of that would be this way. This is the component. This is the component which is perpendicular to your area. So let's call that Pn for normal. Next, this force which is along the area, parallel to your area, that's shear force, right? That's PS. Okay, so we have your general force here. These are your normal forces in relation to your area, and then this is your shear force in relation to your inclined area. Okay, so concerned with normal stress, so I need the normal force. Okay, so let's create our equation. So stress, general equation for stress once again is F over A, right? And then from that, we can get more specific. This is normal stress, so we're concerned with P, or in this case, I've written it as Pn. And then your A, area in question, is actually the slanted one, so small a. Next, we need an equation for Pn. To get that, we use the relationship of the given angle to our figure. Okay? So recall your perpendicular angles, right? Okay, so okay, so this line, okay, is perpendicular to this line, right? What else? This line, your Pn, is actually perpendicular to your slanted area. And recall, if you have perpendicular angles, angle between them is equal. So if this is theta, this is also theta. Once again, let's take this angle right here, okay? This red arrow is perpendicular to this line. This Pn is perpendicular to this line. Angle between this is theta. Therefore, angle between this should also be theta. Okay? Okay, let's do that. So that is theta. Now, recall for components. Components are just the legs of a right triangle, your force being the hypotenuse. So if I draw that, we get something like this. Okay? So let's zoom in. So now let's call this P. Okay. So let's call this P as well. I have a right triangle. If I try to blow that up, we have something that looks like this, right? Okay, this is your theta. This is your P. This is your PN. This is your PS. And then from this, we have a right triangle I can use for trigonometric functions to solve for Pn. I'm given P, I'm given theta, so to get Pn, I can just use cosine. Call cosine theta equals adjacent. Adjacent is Pn over hypotenuse, which is P. So Pn is just P cosine theta. So this is P cosine theta. Now, the problem is, how do I get A? Okay, so once again, looking now at this right triangle, okay, you have this, okay, so using cosine as well, cosine theta, and cosine theta equals adjacent, so again, considering this right triangle, adjacent to this angle is A, capital A. Hypotenuse of this right triangle is your small a. Yeah. Therefore, small a is A, capital A over cosine theta. Just sub that here. A over cosine theta. So simplifying, we get sigma equals P over A, cosine times cosine, cosine squared theta. That's your equation for normal stress on inclined plane. Where A, once again, is the cross-sectional area. So you don't even need a slanted area to get it. Okay. Now what about for shear stress? Same thing. Our equation now is V over A. Recall from your physics, right? Shear force. If you discussed it in your physics, it's just force, parallel force over area. We can use it as V over A, V being the parallel force. Or if not, you can just say, you can first use the general equation F over A, then get more specific. That's actually PS over inclined area A. Okay, now let's get the equation for PS. So once again, using this equation, rather using that figure, we can conclude using sine. So sine theta equals opposite, which is PS, over hypotenuse, which is P. So PS is just P sine theta. So PS, P sine theta over, again, A is just capital A over cosine theta. Simplifying, we get P over A sine theta cosine theta. Now, to simplify this, recall in your math class, identities, double angle identity, sine 2 theta equals, can anybody give me what is sine 2 theta? Anybody remember this identity? No one? You forgot already from your math classes? Very good, Beatrice. It's 2 sine theta cosine theta. 4 points. So 2 sine theta cosine theta. Therefore, sine theta cosine theta is sine 2 theta over 2. So subbing that there, we get sigma equals P over, so we have 2 here, so I'll add it here. So P over 2A, and instead of sine cosine, we get sine 2 theta. And that is our equation. Let's compare. Yep, P over A cosine squared theta, P over 2A sine 2 theta. Okay, any questions so far? Please answer in the chat. How about the others? Please answer as well. Do you have any questions? Okay, great. Let's continue with our topic. Okay, so we're done with that. Now let's talk about the analysis of it. So stress analysis specifically for trusses. So after the actual force has been found by either method of joints or method of sections, the average stress in each member can be obtained from sigma equals P over A. So that's the reason why we reviewed method of joints and sections, because we're going to use it again here. So after figuring out the forces in each member, you can also get the stress in each member using the equation sigma equals P over A, where P are the forces you've solved for in method of joints and sections. Okay? And then we have a few design considerations. For purposes of design, the computed stress must be compared with the allowable stress, also called the working stress. To prevent failure of the member, the computed stress must be less than the working stress. Okay? Or also known as your design stress. So working stress is the strength of your material, okay, how much it can hold. So you'll use that value mostly in your design subjects if you have some. Okay, so your RCD, reinforced concrete design, steel design, you'll use this allowable stress and working stress a lot. For us, you'll mostly be solving for the actual stress, the computed stress on a member or on a structure. You're going to compare the two. Computed stress should always be less than your allowable stress or working stress. That means your design is safe. Okay? If your computed stress is greater than the working stress or allowable stress, your structure is prone to failure. Okay, so that's your design consideration, and that is why we solve for stresses. Okay. Do you have time for an example? Okay, I'm gonna end it there. Next lecture meeting, we'll have examples. Okay. So I don't want to rush things, so I won't give you this example right now. Next meeting Saturday, you'll actually have your diagnostic exam. For those who were absent last meeting, the diagnostic exam. If you want to get details, go to your Blackboard, go to Zoom recordings. You'll find it there. Watch that. Also, go to lectures and then read them. All the details for this course is in here. Okay? And then, as you can see, I've already uploaded lectures for today. So you can advance study them if you'd like to. Anyway, to summarize, Saturday, diagnostic exam. Okay? Coverage is MEC30 topics or statics of rigid bodies. Time is from 3 o'clock to 4:30, our class time. Okay. Open camera, so we'll have a Zoom meeting on Saturday. No video, no score, so make sure to attend the Zoom meeting on Saturday. And then you don't have to upload your solutions. You just have to answer the diagnostic exam. Okay? That's it. That ends our lecture. Do you have any questions in general? Please let me know. Any concerns, clarifications? None? Sure? Okay. Right. So once again, Saturday, diagnostic exam. Next week, Tuesday, continuation of lecture. Since you don't have any more questions, I'll dismiss you now. See you next meeting. You may go. Goodbye, class.